Hey, welcome back, everyone. Well, where is everyone? I see very few people today, but that's fine. I'll be recording anyways. People who are online, can you hear me? Okay, thank you, Trevor. All right, so let's get started. Today is lecture 2 on um, computer vision, and obviously it's a huge area of research. It's a huge, I would say, field, and we cannot cover everything. And so what I decided to do was like what we did in the previous lecture was covered mostly the basic architecture of a convolution neural network, how are convolutions applied, how do we read in images, how do we extract features, so how to create a feature map, and then eventually how can we train a network, like eventually we have the fully connected layers and apply back propagation like any other network. So that's what we discussed in the previous lecture. Now, today I decided to talk about some of the existing architectures, and the reason being that we would like to use them in some problem. We'd like to apply them in some problem. And as we figured last time, that even with like very small images, the number of parameters that we have to train on and then the number of parameters that have to be estimated can become huge in certain situations. And we can utilize some existing networks, their architecture, their output, and even like these pre-trained networks so that like we can build our own model over them. And so that's why it makes sense to kind of get an idea of like how these models are built and then how can we use them. And like the idea of transfer learning mostly comes these models, they've trained them, and then we can utilize them. We can just pick them up and then adjust them based on the problem we are trying to solve. So that's the whole idea of like why we are looking at these case studies when we talk about computer vision. All right. So what I decided to do was like go over a few classic networks, some of the old ones, and we will see that like most of today's networks, and like there are papers coming out almost every day in this field. So it's like growing fast, and it's like hard to track all the models that are coming out almost every day. So it's important to understand these classic networks because most of the models, as you'll see, that exist today are built on these classic networks. We still have primarily the same structure as this like LeNet 5 or AlexNet. And the only difference that comes about is that either the length of the network is more, like you have a deeper network, you have different activations applied, or like some sort of like update in the configurations because you have like more computational power as compared to what we had earlier. And so that's why we have like more deeper networks coming in. But regardless, the fundamental structure of the networks still stay the same. So that's why I decided to go over like these classic networks. That's the LeNet 5, AlexNet, BGG16, and some of the recent ones. That's like the first one is ResNet, and then the Inception, which is also known as the GoogleNet. So these are the 5 architectures that we'll go into the details of. And I also wanted to cover a little bit of MobileNets, reason being that we need some more efficient models that can run on like smaller devices like our cell phone, for example. And so what exactly do they do in order to make these mobile nets like feasible to run given the computational issues with convolutional networks? So that's why we'll do all of this. And then finally, in today's lecture, we'll talk about transfer learning. And we have covered that when we were talking about RNNs, when we were talking about textual data. We talked about transfer learning, that there are these pre-trained models that we can use, and then we can update them based on like how we would like to use them. And then like that's what transfer learning is basically about. Somebody else trained some network for you for a particular problem, and then you can pick that up. Let's say I'm using some image classification, for example, and then the issue that comes up is mostly like how large a data set do you have? And you might not have access to a huge data set, but somebody else had, and they trained that model on that, and then you can pick that up, but definitely tune it depending on what problem you're solving. Okay, so that's what we're going to talk about in today's lecture. So let's begin. The first, and I've pointed links to the source papers because these are the papers that actually introduce these models. So you can just like go and read further about them. But I'll give you a high level idea of like each of these networks. So if you're like more interested in how they were implemented, what are the results they are getting as compared to other models, all of that details, they appear in these research papers. Okay, So let's begin with the first one, which is the LINET 5, a very popular one. And we discussed a little bit of this like in the last lecture, if you remember. So we saw that picture of a network wherein we were trying to classify the handwritten digits. And if we like read this paper, it's not just the digits, but other characters as well. Let me quickly show you what this paper has. Okay, I want to show you what they're trying to classify first, and then we'll come back to the model. So here it's not just the digits, but there are some letters and some other symbols mostly. So that's what we are trying to do here in this like LINET architecture. So it's not just the digits data, but other symbols as well that we're trying to classify. Regardless, these are images of some characters with certain pixel values. And we are applying a convolution neural network to this as an input. And then we are getting some results. So let's try and understand like what exactly the architecture of the model is, how many parameters need to be estimated, and what exactly are we trying to do in this. Because if we understand this model well, then the rest of the models are just like an update on this, or maybe some kind of a fine tuning of this, or maybe some addition like deeper networks. But I feel like all the existing CNN models are built on this LINET. In fact, like if I remember correctly, GoogleNet actually named the Inception model as GoogleNet because they wanted to include this like LINET 5 in that name, and they wanted to like keep that intact because this was like a groundbreaking model. So that's why. Okay. So going back, let me try to draw. Regardless, like my bad drawing skills, I'll still draw because if I don't draw, then I'm not able to explain. Okay. So let's say I'm trying to identify this digit 7, right? So this is an image. And usually, if I remember correctly, in MNIST, it's either 28 by 28 or 32 by 32. I don't exactly remember, but something close to that. So 32 by 1, because these are like black and white, so you don't have like a 3, right? And then in the very first layer, what they're doing is they're applying 6 filters, okay, and 5 by 5 filters. Now, from our previous lecture, we know what the output is going to be because these are 5 by 5 filters, 1, and then there are like 6 of these. So you'll have like parallel 6 outcomes, and then I'm going to stack them. So I'm just skipping that part where we used to do a convolution for every filter and then do another step for stacking them because now we understand what's happening in the output. So I'm just going to write the output, right? So this comes out to be a 28 by 28, and because 6, so you have the 6 stack. And we are going to follow that like throughout in today's lecture, right? So that's that. And then one important, like the details that I want you to like take away from this architecture is not like what is happening, how many filters are applied at every layer, or like what convolution I'm applying to every layer, because you can definitely refer to the paper and like that's not something to remember. But things to remember are like what non-linearity is being applied, how many layers are there, like high level, because this is not a very deep network, because that also points to the number of like parameters that you will be estimating, right? So these are the key takeaways. You don't have to like memorize this, and I have this like drawn on my notebook and I'm just like copying it. So even I don't remember, so you don't have to remember. But that's the fundamental idea. And then also like some details, like we talked about max pooling last time, right? But this network, this was like one of the earlier networks, it did not use max pooling, it used average pooling. So these are the important details of this network. So here, once I have this stack, right, I'll have average pooling instead of max pooling. And max pooling is more popular right now, but apparently in those days, average pooling was applied, and the paper talks about like why they do it. So we can like go over that, but let's focus on the structure right now. And then again, here they apply like 2 filters and the same size, 5 by 5, and then a stride of 2, right? And then we get a smaller 14 by 14. Eventually, we get a 14 by 14. And let me just like skip the rest of the layers. I think it has like 7 or 8 layers, or we can check the paper. But the point that I'm trying to make here is that with every subsequent convolution and with every convolution, average pooling, convolution, average pooling, eventually we arrive at this structure, which is just like a 5 by 5 by 16. And we know like why we are interested in getting such a structure, because we have subsequently reduced the I would say the spatial footprint, right? But keeping it intact, because that's what the whole point of a convolution was. I'm keeping that intact, right? The spatial footprint of the image, but I have like that intact in a lesser number of features. So that's my feature map has the reduced length and the reduced width, right? But it has this like elongated, because I've included more number of filters, right? So with that, I have like more depth to my network, but like my feature map has gone down. But just like think about that, I have like more feature map stack, but the size of the feature map is smaller, right? And why do I need it? Because eventually I need that like one-dimensional for the fully connected layer. So there are two fully connected layers finally in the network. Once I have this, then that's fed into I think 120 and then 84 neurons. Again, fully connected. So let me just name them FC. And finally, a softmax. But I think there are like 10 possible values if we are doing it only for digits, right? 0 to 9. If you're doing for more, then it depends like how many possibilities we need. All right. So the thing is that this was like one of the first very deep networks that was used for images. That's like one. The other thing is that like in every convolution, remember we said that we apply some non-linearity to every convolution last time. And usually that non-linearity is a ReLU in more recent networks. But what this network was doing, like for every convolution, we are applying this non-linearity. And that non-linearity is sigmoid or tangent. So that's like one major difference between networks of today and this one. The other one is that this thing, this like with every subsequent layer, we have like some number of parameters. Obviously, we have like this convolution idea. We have applied convolution because we want to bring down the parameters. But regardless, this has like 60,000 parameters to be estimated, which is pretty low because like in today's networks, it's in millions. So that's low. And so obviously it impacts the performance, but regardless, it gives a good performance with like this MNIST data set. Okay, so let's quickly jump to the paper now that we understand like how the structure is, and they have a better drawing than this one. So that's why let's look at it again. So here is the network, and this is for digit recognition. That's what they're saying. Each of these is a feature map, and how this eventually comes down to the fully connected layers, and then finally the output. So that's what we discussed primarily. And this paper also talks about like how the training happens and what all like performance it gives. And it seems like in those days, this was like a pretty good performance by all standards. But then later, when we started getting more computational efficiency in terms of the hardware, in terms of the amount of research that has been done, progress that has been done in hardware, like we have ways to train bigger data sets, deeper networks, and faster. So obviously, the networks of today are way better than this, but like this one in those times was pretty good. Okay, so this is something that you must remember. Like LINET 5 is the basis for all the other networks that come later. Okay, so that's that. Any comments, anything that you wanted to add? Yes. I think it was in the 60s, as far as I can tell. As far as I remember, it was in the 60s. Okay, so the next network that we're looking at is AlexNet. And yeah, that's a nice name. Remember that. And what it allows, like in addition to what LINET already has, it allows for a more like high resolution image processing. So basically we'll be using bigger images with like, so what does high resolution essentially means? I'm not using a 32 by 32. I'm using a 224 by 224 by 3. So that's huge. Like just one image has like, and remember how we do the convolution, regardless of like however I'm doing it, I'll still have a lot of parameters because I want to maintain the spatial footprint, right? So that's what AlexNet proposed in this paper, and I think it is quite evident in the structure. I'll quickly show you, and we'll talk through this, like how how is it structured and everything. But what they're doing is like there are two parallel networks, and they haven't like there isn't a complete picture of the other one. So if you just look at the bottom one, let me just. If you just look at this part, right? There is this like whole network here, right? Just like if I draw a line, right? And then there's a parallel network up there, like a replica of this one, the one that's at the bottom, right? So what they're doing is that they're training like two parallel networks, but together, like they are like able to handle a lot of parameters. But again, like if you look at the overall structure, it is pretty similar to the Net 5, but it is deeper and it has like other differences, like the non-linearity is again different. It's not the sigmoid or the tanh. And also like they are applying max pooling as opposed to average pooling that was applied in Net 5. Those are some of the differences, but the major difference is that you already have like two parallel networks that are being trained on like two different GPUs. That's the fundamental difference. The rest of like the structure is something that we have looked at before. Let me quickly go over the structure regardless, because first of all, this is like, if you look at this input, this is like 224 by 224 by 3. So that's huge, right? And then in the second one here, what we do is we apply like 96 filters in the very first layer, not the second one. We apply 96 filters that are size 11 by 11. So that's what this is showing. And because why they're showing like two different filters, because there are two different parallel networks. And that's how they are like representing it. Yes. So remember what we said in the last lecture that deciding the number of filters is a hyperparameter for us. So of course it depends on a lot of factors. For example, what application you're using, and eventually the weights of those filters will be learned by my backpropagation algorithm, right? So I will initialize them, but the good thing with transfer learning that, as we'll see today, is that somebody else initialized them for me and even ran the entire backpropagation multiple times. And I do have a starting point now, if that makes sense. Yeah. Other questions? People who are online? Okay, I'm sorry. I just forget that like we have students online. Okay, if you have questions, just like type in the chat and I can go back to that. Okay, in addition to max pooling, this network also, because in the Linet 5, we're not using any kind of padding or stride, but in this one, we are using a stride of 2 for every convolution. If something happens to this pen, a stride of 2. And then we also have padding in some places, but not like in every layer, right? So those are some of the additional features that are added here, in addition to what we already had. Now, obviously, as you can see that we have like these two parallel networks, and because we wanted to make our computation faster, and so that's why we made like these two parallel networks. All of that is good, but because we are already using a high resolution image, and eventually when we've passed through all the convolutions and all the filters, we will end up with a higher number of input values to the fully connected layer. So as you can see, like we have like 2048, which is like way more than the one that we were earlier, like using earlier. But the reason being that we are using high resolution images and we have a deeper network. So once we have like this 2408, we again have like a fully connected layer, and then we have a soft max. So this one here is a soft max with 1000 outputs. And if I remember correctly, I don't remember the data set they used. Let's quickly check which data set they're using. Yeah, that's what I thought, but still wanted to confirm. So ImageNet is the popular data set in computer vision. And so that's the one that they're using. And they have like 50 million labeled high resolution images. And that belongs to like 22,000 categories. So that's huge, humongous. And so as like compared to the Linet 5, this one really performs well on this particular data set. And you can tell that this is like high resolution images as compared to the MNIST one. So it's not as easy to like train this one like on this data set as compared to the other ones. Now, there are two like fundamental differences. The Linet 5 was trained on MNIST, while this one is trained on ImageNet. And like going back to your question, let's say I'm working with like higher resolution images. And so most likely I'll pick this as my base model and then go from there, right? If I was working with the digits data, most likely I'll pick the LeNet 5 because I don't need to add so much computational power and other things to my model because that's unnecessary like usage of that like computational power, right? So those are some of the things that we need to keep in mind when we like start to train our own model. The other thing that it's like very similar to LeNet, but the number of trainable parameters, because we just saw here, right, increases to the number, I think it's 60 million. So from 60,000 to 60 million here. So the number of parameters that need to be estimated, or the model, the weights that we are estimating through our model is around 60 million. So you can see the difference, like from 60,000 to 60 million. Okay. But then that's doable in today's age, thanks to some great advances in hardware. So that's doable. But yeah, definitely there is cost to it. Okay. All right, that's this one. Also, yeah, so this is what, yeah, I remember it correctly. So 60 million parameters are there. And there are 1,000 classes. Okay, for this, it was for this competition. I think it was a winner or something in this competition, but I'm not 100% sure. Okay. So we will talk about data augmentation towards the end of today's lecture. Like this is one technique of how can we deal with overfitting when we are talking about image data. So data augmentation is an important addition to image processing and like convolutional neural networks, especially when we are dealing with overfitting. So we'll talk about it towards the end. Let's like leave it there. And yeah. Okay. So those are the two important classic networks, LeNet 5 and AlexNet. Let's move on to the third one, which is the VGG16. I'm sure you must have seen that word somewhere, or you must have heard about it, or you must have seen like in some of the import statements somewhere. I don't know, like maybe you have, you haven't. So this was, yeah, this was a winner of this competition in 2014. And this is a pretty famous competition in do I have the name right? I think ILS VCR or VRC, something like that. I don't remember the exact name, but yeah, it was a winner. And let's see what exactly this network is. This is VGG16. This is also known as the Oxford Net, and it's a CNN, obviously. And it's named after the visual geometry group from Oxford, like the team was named VGG, and that's why the name of the network. So let's look at like what this particular network looks like. And okay, so why was this like an important network, first of all? The reason being that we saw that this AlexNet, of course, it's like giving good performance with high resolution images, but it has some issues with the number of parameters that we just saw, right? And it's like hard to train in terms of like the computational efficiency that you require, like wherever you are training, and then the amount of data that it requires. So those are some of the issues that are there. And then the architecture is pretty complex that way. Of course, like we have these parallel streams running, and that makes it a little bit better. But then with VGG16, what they're doing is that they have defined a very simple architecture, a simple architecture which is deeper. Okay, so depth helps when we are training images because with like just like we saw with LeNet 5, actually, like with every increasing like layer, you are reducing the number of features. You're definitely adding depth or the number of channels, but then that makes the number of like features go down in some ways, right? So depth helps in a lot of ways. We'll see that it has its downsides as well. So what this VGG16 is doing is that it has like a simplified architecture in the sense that you don't change the convolution filters. You don't change the size of those. You just keep them the same. You just like change the number of the filters in every layer. So remember what happened when we changed the number of the filters earlier. It would just amount to the depth or the stacks that we add at the end, right? So that's exactly what this is doing. And let me give you a high level overview of like what this is doing. Of course, no need to like memorize it, but quickly see what's going on. So first of all, at every step you're using like a filter of like size, let's say 3x3, or maybe it's 2x2 at some places, but it doesn't change a lot, right? You keep a stride of 1 and same padding. You don't like use any padding at all. And max pooling, after every convolution, you're using a max pooling, which is like a 2 by 2 with s equals 2 for the max pooling part. Just let's focus on like what's happening in a high level. So let's say I have like this image, right? This is my input high resolution image. So let's assume this is like 224 times 224 times 3. And by 3, I mean it's an RGB, right? And what I do is I apply this convolution, whatever filter I have, which is like 3 by 3. And I use 64 of these. So a huge number of like small filters. Now, what this is going to do is it's going to somehow retain this, right? It's not like maybe it will change or not change, but eventually what will happen is that this thing will start to go down. For example, in a couple of like steps, you will have something like 112, and so of course there are more steps here. 112 by 112 by 128, and then this goes on for I think 56 times. Okay, no, that's not correct. So then it goes on, and I'm going to show you in the paper how this goes on. Then eventually we reach at something like this. Yeah, so this is the final output that we get. So we are down from like 224 by 224 to 7 by 7 by 512, just by like having more number of layers. And to be precise, if we are talking about VGG 16, 16 refers to the number of layers. So you'll have like 16 layers here. And what they show in the paper is that they train networks from sizes like layers 11 up to 19, and then they find that the 16 layer performed the best. And so that's why they chose like VGG16. So again, what this network adds to our knowledge is that this is a more simple architecture as compared to like creating different convolution sizes at every layer and then capturing that, but rather just like keep that constant, only change the number of the filters at every layer. Make the like, okay, so simple architecture, these are some of the key takeaways. Deeper network, so because you have like more layers. Yeah, simple architecture because we're not changing the size of the filters. And then eventually you like at this point, like in the final layer, you get around like 4096, right? 4096 values in your flattened out vector, right? And so you're going to like feed that into your fully connected layer. So fully connected 1, fully connected 2, and then a softmax. So rest of the structure stays pretty much the same if you look at it, right? In fact, like most of this has been very similar from like LeNet 5 up to this VGG16, except the number of layers, except the way we are like doing the convolutions. And of course, if we think between LeNet 5 and AlexNet, AlexNet was like more complex in terms of like the number of layers and the difference in the convolutions that you're applying. But in this case, we have actually simplified my network. I've like subsequently simplified it because I'm not making a lot of changes to my network. So yeah, so this is a 16-layer network. Overall simple architecture. What they're like, yeah, one more thing, they are like having a simple architecture, deeper network. And at every subsequent layer, we are doubling the number of filters. So that's another thing I think about. Doubling number of filters, but not the size of the filters. Okay. Okay, so all of that is good. So what is like one downside, because I've added more layers? So you can just tell by looking at it, because I've added more layers, there must be a downside to this. And what do you think is the downside? Yes. Training time, that's excellent. So that's the time, right? Anything else? What exactly are we training for? Yes.
I was going to say finishing gradients.
That is going to be one, and we're going to discuss that. So yeah, gradient problem can come, and why? So that's actually pointing to the very fundamental thing. Why are we like headed towards that? I think that's because like imagine the number of parameters we are training at every step that gets added. Everybody agrees with that? So the number of parameters that I'm training is like around 138 million. Yes. So that's it. And both of these actually point to that. right? So that's the bigger like downside, right? And there is like a VGG19. And so imagine that it goes like even beyond that. And like in the paper, they actually did that. They trained the VGG19 as well. And then they found that the VGG16 was doing way better. And so they selected that one. Okay. And if I remember correctly, this was the one that was there in the in competition with the GoogleNet, and this did achieve good, like in terms of the accuracy, it was really good. Things slightly less than GoogleNet, but otherwise good. So it did perform well, but then it has its downsides. Okay. So let's quickly jump to, and then we are going to address these two issues like time and gradient and how can we make them better in this. Okay, so yeah, as the name suggests, very deep convolution networks for large-scale image recognition. And I don't remember if they have. Okay, so they have it in a tabular form, which is why I wanted to draw that. But eventually they come down to this. That's what we said, right? So eventually they come down to these number of parameters. They're just showing the configuration here. Let me see if they talk about the number of parameters. And what data set were they using? Let's also figure that out. Was that the ImageNet one? Yeah, so that's like what the abstract is also telling us. It's like a 3x3 convolution filters. They don't like change that, but they just keep pushing the depth from 16 to 19. This was part of the ImageNet challenge. So maybe we can like go to the ImageNet challenge 2014 and see what data set is there. They must have described it somewhere, but don't want to spend too much time. As far as I remember, it has to be this ImageNet data set, but anyways, yeah. So here they're like they're comparing like different VGG configurations and also with other models and see like how the performance was. And as I said, the performance was pretty good. And then like you can tell I'm training like 138 million parameters. So the expectation is that I need to get a good like outcome from that. That's what happened here. All right. So I've provided the link again, and you're free to like go and read these three papers. I feel that they would be a good addition to your knowledge, and specifically if you're planning to work on using any of these networks for your final project. I know a couple of teams are, so that would make sense that if you can just like go and read these. All right. So a very good point that came out of specifically AlexNet in VGG16, and most of you rightly pointed out, is that like the issue of efficiency in terms of like the time it's taking to train these networks. And also this issue of like vanishing gradients and exploding gradients problem that we have seen before, right? And so that's why there is something that's known as ResNets or residual networks. And this is like a classic neural network used like as a backbone for many computer vision tasks. So we'll see how this model can actually help us. And this was like one of the winners of this ImageNet challenge in 2015, right? And as you must have noticed, like most of these networks are coming out of like these image competition because like in the last 10 years, and believe it or not, like most of these recent models have come out in the last 10 years or so. So they're pretty recent in terms of like when they were devised, and also because we have better capability in terms of like hardware now as compared to what we had like 20 years ago. And that's another reason why we have like more of these coming up. Okay. So coming to this like residual networks, what exactly do they do? And how are they more efficient? How do they actually help us like learn better and take less time, right? And also sometimes deal with the vanishing and exploding gradients problem, right? So as you rightly pointed out, major issue posed to some deep networks is like the vanishing and the exploding gradients problem, right? And in image-related tasks, there is this added issue of convergence due to complex loss surfaces. That's another issue that the optimization part is not that well captured in my learning with my learning algorithm. Reason being that these, because of the way the like an image input is, I might not get a very good result in my optimization algorithm, right? So those are some like, it doesn't converge in some cases. So we needed to figure that out. And what people figured in many of the research papers is that if you consider like this thing, this scenario, so you have like an image, of an animal or a dog, right? And that animal is like standing inside a square frame. Let's say it's an elephant, maybe. I don't know. So if you just like imagine that picture, and I tried to find that picture, by the way, I couldn't like find a good one, so that's why I didn't put. And I thought I'll ask everybody to just imagine. Okay, so now that you're imagining an elephant inside a square frame, and there are some intricacies to that image, like some of them are very complex, like things to learn, for example, the eyes or the trunk portion or the face portion, right? And then if you think about the square frame in which the elephant is standing, that's pretty simple to learn, like it's a square frame. So there are like these different levels of complexity to an image. And like if we have a complex network, we are just like using the same level of abstraction, if you think about it, for almost everything. Because like if I apply a convolution filter, I just put it like on every part of the image and I get the information. And then I'm adding depth because I want to learn the intricacies of my image as I move forward. But like some parts of the image were not like, did not require all that intricacy. It could have been done with a shallow network. I didn't need it. And most of the images have this issue, if you think about it, right? Some parts are like pretty simple, but some parts have like these details that need to be learned. So in order to like, with that motivation in mind, this ResNet, it introduced something that's known as a skip connection, right? So we'll see what this does. It actually skips certain layers, and I'm going to show you like visually what that means, but just try to understand that we're skipping certain parts. Now you've seen that kind of an architecture before. Anybody remembers when we were trying to skip things and not include everything? Okay, that could be one. In deep networks, we did something where we were trying to pass only the information that was relevant. So we were putting some gates, remember, in some networks. Anybody remembers that? You remember? Okay. Anybody else remembers? Only one person remembers. That's bad. Okay, so then let's go back to RNNs. Remember in RNNs, we said like when we were using contextual information, we had the LSTMs and the GRUs, the gates that we added. Why? Because we want to restrict some of the unimportant information, but we wanted to like capture some of the important ones. So that's the same idea that this skip connection is going to do, right? So the skip connection will provide an unlike impeded gradient flow for some of the information, but it will not let like the other information pass through all those deeper like layers. So that's the high level idea. And let me show you what that does with a very simple example. And then we'll go into the paper and see like what exactly it means. But okay, so let me just like think, and A is for activation, like because I'm carrying it from the neural network lecture. So this is like any activation, and then you go inside some layer. So let's assume this is some layer, right? And then the activation that comes out of this layer is L+1. And then you have another layer, and the activation that comes out is AL+2, and so on, right? So what we do in a skip connection, sometimes also known as like a residual block, is that I won't just pass this information like this, like sequentially, but I might skip like some of this information from here and go here. And this information is applied to this layer before I apply the nonlinearity. So before I apply the ReLU or the sigmoid or whatever it is, right? So this is exactly what we are doing. What we are like in this ResNet architecture, we are skipping some of the layers as we are like training our network. And we are, okay, so how does that help first of all? And before that, how is this applied? So let's try to understand that first, and then we'll see how does that help. So like if you remember, there were two steps in every network, and that stays like universal. The first thing is like you have this Z for layer L, right? And so that was what W transpose X plus B, right? So that stays as it is. And this is for layer L. Instead of X, remember, I usually denote it by A because it's after activation. So A, but from the previous layer, and this could be X for the first layer. That's it, plus B of L minus 1. Yes, L, not L minus 1. And then finally, we have A of L, which is the activation. ReLU over ZL, right? This G is ReLU. Okay, so these are the two steps that you're doing like in every like in every step of your like fully connected layers or the previous layers. That's what you're doing. So basically what's happening in every subsequent layer is some kind of like this linear summing up and then activation, linear summing up and activation. So if you think about like the number of steps that you would have done to go from here to here is roughly speaking 6 or 7, something like that, right? Because you're just like doing 2 steps at a time. So a lot of operations if you go from L to some L plus N or something. That's the point that I'm trying to make. So what we can do is we can take a shortcut for some of the inputs and just like skip these different summations and these values that I'm applying. And rather what I can do at this AL plus 2 directly is that I'll have G, which is like a ReLU obviously, ZL plus 2. So this comes from like what we've been doing until now, right? We obviously do this all the time. Whenever we are applying some activation in some layer L, which is L plus 2 in this case, I always do this, right? I apply a G over this. That's all I do. But here I'll also do something like this. So I will take this input from AL and also like apply to this input, and then I will like sum them up, right? So that's the additional step that I'm applying. So I'm letting like some of the information pass through by skipping these like layers. And it could be more than one. I'm just saying that I'm skipping one, right? But it could be more than one. It depends. There are different configurations of this ResNet that allow like skipping different numbers and skipping at different, start the skipping maybe sometimes later, start the skipping sometimes earlier and so on. Right? So this is known as a skip connection, and this thing is known as a residual block. Okay, and it is shown to give like a very good performance with tasks wherein you have like intricacies in the image as well as like some simple things that are together in the image, and then you can learn both of them. So how is that actually helping and why is it working? Because like, okay, this tells me that I skipped some information, but then why is it working? Like, that's the big question, right? And we need to understand that, but let me show you the entire network and then we'll come back to this part and see why this works. So for, if you see this part and like I try to summarize the paper. So what they're saying is that like the skip connection provide a path of unimpeded, so like unstoppable kind of gradient flow for some part like of the image, while for the others it lets it like learn slowly because you still have those connections there, right? And so what happens is that's really good for the back propagation because sometimes when you don't need to like go through each and every intricate step, you can just like skip them for the simpler ones. Because what actually happens when I'm trying to learn a square? I can just do that in a single layer maybe, right? So I don't need to go through all of the layers that are there. But then if I'm trying to do some kind of a facial recognition and both are there in the same picture, I do need to go through that. So in some ways, think about like I'm doing both the things in like together, right? And I'm going to show you mathematically how that works, but let's first, yeah, so that's what this section talks about. Like inputs can be classified with a small amount of linearity, non-linearity will skip many connections because the weights will go to 0. I'll show you mathematically what that means, but the weights go to 0. So basically what happens for those types of inputs is that like at AL plus 2, you're still having AL. At AL plus N, you still have AL because the weights went to 0 for that, and then there wasn't much to learn. And so you just skipped them, right? So let me quickly jump to that. Okay, and this actually was does provide a lot of improvement, like a huge amount of improvement as compared to the networks before. So that's like a big, I would say, achievement of this model. Let me quickly show you what it does. So this is showing you what a residual block or a building block looks like. Okay, and let's, yeah. So here it is, and I don't know how to show you this part. So this is like they're comparing it with a VGG19. Let me make it bigger maybe. But I wanted to show you the entire thing. I don't know how to. do that. Okay, and then magnify that. Okay, so here is a comparison of like VGG19, 34 layer plane. By plane, they mean like a normal CNN that we have seen before with exactly 34 layers. And then they have like exactly 34 layers, but a residual network. That's what they're showing. And so this plane was also trained. And in addition to that, this one has like 2 skip connections. So just like notice any of the residual block, they're skipping 2 connections in every step. And then eventually, I think they apply a max pool, okay, average pool, and then a soft max. So that's the final layer, right? Because obviously we're using it for ImageNet data set. All right, so this is shown to like give really good performance as compared to the VGG19 in terms of the computational power it requires. It requires really less power as compared to what we were using with VGG19. And also like in terms of the efficiencies, and that graph really shows that. Yeah, so maybe I can give you a high level idea of like what this does. Usually what happens with the training error, that usually goes down, but remember the test error sometimes dips and goes up usually. But for the ResNet, the test error also goes down for like a long time until it like begins to rise. So that's the fundamental like difference between other models and ResNet. So the question arises like, why does it work so well? And this concept of skipping these cells or these like layers is known as residual learning. And why it helps is because like you are letting the intricate or the more complex weights to pass through this all the layers, but then you're letting the smaller ones or the easier ones to skip. So then they learn faster, right? And there are multiple paths through which you can have your learning algorithm being trained. So all of that is there. And let me show you what actually happens when we like apply this to big networks. So what's really going on is something like this. Okay, so I have like some input, and then I won't draw that. Let me just write like some big network. We already are aware of like all the layers. And then eventually somewhere in the middle, you have like some AL, and then some more layers, and eventually you have like AL plus 2 or plus 4, whatever, right? And so this is, let's say, a ResNet. And so we skip here and we go here, and this comes out here, right? And so let's say the function that you're using here is ReLU. The nonlinearity that you're using is ReLU. And remember what I said about AL plus 2 is like ReLU applied to ZL plus 2 plus AL, which in turn means that this part can be written down AL plus 1 plus BL plus 1 plus AL. Okay, so in cases where like in situations where like these are extremely small, these go like really small, they go to 0, let's say, right? And they're like more regularized, these inputs, right? So they don't have a value because of like they were very simple to learn, maybe, right? And so what this will give me is like ReLU and AL. So basically my new AL plus 2 is essentially, and if like this is greater than 0, then for ReLU, it's like almost like the same thing as AL. AL plus 2 is again AL. So in some ways, what I'm doing is I'm replicating this layer after like 2 to 3, like after skipping 2 to 3 layers, rather than let it go through the like 2 different nonlinearities and then make the values like diminish to almost 0. Right, so I have like these multiple paths through which, like when, just imagine what happens to the back propagation. When my learning algorithm works, then I have like these multiple paths that my back propagation would happen through. And I will have both the options wherein I'm like skipping as well as like I'm going through the entire network. So the entire network still acts like as some fine tuning thing because I do have that option of like training the entire network, but I'm also having the skipping part so that in many images, it makes my life easier because let's say many of the images were like pretty simple. So I don't need to go through the entire thing. And so my training overall is faster, right? So I'm keeping both the options here, but like this is what a residual network does to the skip options. Okay. And so that's like precisely what they also talk about in this paper. I think, where is it gone? As far as I remember, they do show results. Yeah, so here are the results. And this one here, the first one is actually showing us, okay, here's a comparison of like what happens when we are adding depth to a plane network. And here's what happens when we are adding depth to a residual network. So as you're adding like a depth to your residual network, and this is like the red one, this red bold line, and then the green line or the blue line is the shallow, like comparatively shallow network. So the training, I think is the test error, right? Or the training error. Okay, so the training error keeps going down. So well, that's a no-brainer. Training error usually goes down with more deep networks. But the important thing is the comparison between them. So even with like a deeper network, this one is like performing well, because if you look at this like plain network with the 34 layer, right, it starts to perform like bad beyond like some number of iterations. Yes. Yeah, I think that's what I'm like also confused. So the thin curve denotes the training error. Bold is the validation error. Yeah. Yes, that's right. That's right. Yeah, but I think the graph here is more towards like comparing what happens when I make ResNet more like deeper versus like when I don't make it deeper. But like also not just like it's faster, but in some ways it is dealing with like some of the issues that we talked about earlier, right? So for example, the issue of vanishing and exploding gradient, because if that's the issue, then I can skip like more than 2 layers. I can skip as many layers as I would like. So I think there is another paper that talks about many different configurations of ResNet. I couldn't find it, so I couldn't put the link to that, but I'll definitely try to find it and like add that link if you're interested in that one. All right, let me see if I missed anything about ResNets. Yeah, one thing, I think that's in the paper, so I wouldn't write it down. Because sometimes when we're doing this, I don't know, because it's so complex, there is this thing that there's a trick that we need to apply at some places. So for example, like this y is actually some AL plus 2, right? And this is my AL, right? The dimensions might not match because I have skipped many layers and the way my convolutions were applied. And so that's why we need to sometimes do this trick of adding this like matrix WS so as to balance out like, so maybe it could be an identity matrix or something like that so that we can like make the dimensions equal. So that's a small trick that's important. And yeah, and like because of the same convolution sometimes, so like ResNet also has same convolution, so we are mostly able to preserve dimensions. But if not, like if you've made some changes in your configuration, then just add this like this small square matrix. I think it has a name as well. Yeah, to match the dimensions. That's the small trick that we do. All right, so this is one of the more recent networks. And if you're working on any image recognition type task, you might want to explore this one because it gives like, it's pretty efficient that way. The other one that I want to talk about is GoogleNet. And maybe let's take a 5 minutes break and then start talking about like this Inception network. All right, let's get back to two more networks, and I promise I'll let you go after that. So this one is important because this is the Inception. This is also known as the Inception network. Believe it or not, actually inspired from like one of the memes from the movie Inception. Yes. And so, yeah, so that's why it's named Inception, also known as like GoogleNet architecture. So this architecture has 22 layers in all, and they try to reduce the like the depths in some ways, and also try to deal with some of the issues that the network before this had. And like the overall architecture is more like a parallel kind of a structure, but then they figured that that parallel structure also had a similar issue of like more parameters. And so they come up with an alternate structure. So let me show you like what they start with, and then where the issue is, and then like what's the update that they applied. And let me draw it here. So what they're doing is maybe like having multiple layers in sequence. Why don't we have like all the layers in parallel? That's the idea here. And so let's say I have like a, I don't know, 28 by 28 by 192 input. And what I can do is I can take it like in different ways. So maybe I can apply a 1 by 1 convolution. Maybe I can apply a 3 by 3 convolution, and maybe I can apply a 5 by 5, and I can apply max pooling as a parallel option to this input, right? So I can do all of those, and then eventually I'm going to get like some outcome depending on like the number of filters I'm using here. And so I don't remember exactly how many. Let me assume that we have 32 filters. We can check the paper, but like let's say you get 28 by 28 by 256, or okay, let me check the third one because I don't remember the number of filters we are using here, but regardless, you'll get some output here, right? And what you're trying to do is you're at least trying to maintain the first two somehow, right? So you're not like, so the way you're trying to do like this filtering is that you are trying to have the same what do you call them? The first two dimensions. Obviously, you can stack them by doing some kind of like manipulation to the number of filters you're using. So why are we doing this, right? So why are we getting like these multiple outputs? Well, the idea here is that how about I parallelly like train these models, these four or five models, and then I stack them all together. So basically, you will just like have a stack of like all of these together. That is going to be your like combined output. And that combined output is known as the Inception module. That's the fundamental idea, that you just like have these parallel filters or parallel convolutions that you apply to the same image, and even max pooling for that. And then eventually you do some manipulation so that you get like the first two dimensions at least the same, because remember the third dimension is the variable one that depends on the number of filters, but you can stack them one over the other because the first two dimensions match. Right, so that's the final output that you're going to get. That's the final output that you're going to pass on to the next layer and so on. Okay, so what's like the issue with this? Everything looks good because you're like almost capturing every aspect, every intricacy of the image, because you have like both like smaller sizes parts that are captured by 1 by 1 convolutions. Then you have like 3 by 3 sized parts that are captured by the 3 by 3 ones, and then the 5 by 5 and so on. So the whole idea was to deal with the same issue as ResNets in some ways, that there are certain parts of the images that are like simpler as compared to the more complex parts. And like by doing this, I can capture almost like everything because I have like these parallel filters with like maybe different numbers. And so I captured everything and I just like stacked them one over the other. Now, obviously, the moment you look at this, you know that this Inception module is going to be a problem, because eventually you have to feed it into like the fully connected layer. And then eventually like you have to feed it to like going forward, you have to feed it to other layers. And then you're going to get some output. So basically the computational efficiency is going to be bad, right? If we just look at one of the paths in this like tree-like structure, even this one, if I had like 64 or 128 filters, this is going to get like really big, right? This is going to get huge. And so again, the same issue comes up as we have seen in other networks of like this computational cost. So that's an important problem. And even if you look at just like any one of the branches, that's a big problem. So the way they solve this problem is by having, of course, we'll have the same architecture, but what we're going to do is initially, instead of like having these variable size convolutions, I'm going to apply a 1-by-1 convolution initially. And then I will definitely apply these larger convolutions later on in the second step. But in the first step, I'm going to apply a 1-by-1 convolution. So the thing that comes to your mind is like, what is this like 1-by-1 convolution and how is this helping, right? Let's try to actually visualize it. I don't remember if I had a picture of this. Yeah, oops, what is this? Okay, so for some reason, this keeps popping on my computer. Really weird. Okay, so let's look at how these like 1-by-1 convolutions work and why are they useful. Let's say I have like a 6-by-6-by-32 image. And remember, the 32 is the depth here, right? That's why this. And then let's say I'm doing a convolution with a 1-by-1. And then this also should have a depth of 32. Remember, we talked about this in the previous lecture, so let's not repeat it. Now, when we get like the feature map using these convolutions, basically I'm placing this like entire like cube throughout, right? And then I'm getting like the one output. If I placed it here, so that's my output. I placed it here, so that's my next output and so on, right? So that's how I'm going to get the output. So one important thing here is that I have like how many, I'll be doing some like 32 computations to get like that one value. So I considerably reduce my number of computations if I'm using this 1-by-1 filter. And the other thing is that, remember, like if I add more depth to this, if I want to add more depth to my feature map, then one way out is that I can increase the number of like filters, right? So the good thing is that the computational cost of this 1-by-1 filter is low. And so I can just increase the number of these 1-by-1 filters and still manage to capture most of the information in any intricate image, right? So that's exactly what we can do here. So let's say I was using 16 such 1-by-1 filters. I'll have like a depth of 16 here in my feature maps. So that's the fundamental idea, that you can keep growing these channels or this depth. You can keep doing that, but still like keep shrinking the features so that you don't have so many learnable parameters. That's the trick that they're using in this particular, I would say, network. That's the GoogleNet or the Inception one. So what we're doing here is that I'll apply this 1-by-1 convolution first. Let me show you another picture. And then we can go back to the actual paper because that has a better like picture, obviously. But let's look at this. So I hope I'm drawing it right. If not, we can correct it. So 28-by-28-by-192. And then what you'll do is you'll have these different 1-by-1 for the very reason that we just talked about, but different numbers, obviously, depending on like what we are trying to do here. And let's say again, 1-by-1, I think 16, 96, and then you do apply max pooling here. And after that, you apply the 3-by-3 that we talked about earlier, right? So then you can apply the 3-by-3 and the 5-by-5. And there are certain numbers that they are using. I think this one is 32 and that one is 128. And in addition to that, they have a parallel 1-by-1 also. I think 64 of these, because like there is no need to do a 1-by-1 and a 1-by-1 again, right? So they have like a parallel 1-by-1 as well. And okay, and this one has, after max pooling, apply a 1-by-1 con. And you can see like what they do is, as I said earlier, they will stack the output of all of these. So now what you get is like a channel concatenation. This is known as a channel concatenation. But this has made my overall processing subsequently faster because I've added this extra layer of like 1-by-1. So I have reduced the dimensions of my initial input, but then I have kept the spatial footprint somehow intact by using the depth to that 1-by-1 filter. Okay, so this entire thing is not my network. This is just my inception block or inception module. So there is more to it. And let's go and see what that more is. So actually, this is just like one block in your network, and you have multiple such blocks in your network. Okay, let's look at the picture and see what that is. Yeah, so this one is talking about like how you're doing the block itself. So I just flipped it. So because we are used to looking at it like from left to right, but that's the exact same thing they're doing here. And yeah, so here it is. How should I make it bigger? Okay, so here, this is the output, right? So we begin from here. Yeah, that's the input. And then just notice any one, and of course, like they have more added steps before, but the fundamental idea is that you have these inception modules added to your network. And just notice like any one of them, for example, this one here, or let me just pick any one up here. Yeah, here, this one is a good example. Also notice like we of course discussed this part. We discussed this part, right? Some input is coming up one by one convolutions and then pass through all of that and then get some concatenated layer and then keep passing that. But we didn't talk about like what's going on here, right? Just notice like there is another kind of an output. And what we're doing is from the previous concatenated layer, right? I'm taking the input and just creating a network of its own. And also like just applying a fully connected layer, like notice these fully connected layers, and then the softmax and getting the output. So I'm also getting some intermediate outputs, and maybe at some like maybe for some particular image or for some particular image task, I don't even need to go up to the end, and maybe I'm getting some results here as well. So that's what they're showing here, that they have like these, and there is like one more up there. So like at every intermediate step also, they're like analyzing the outputs. Right, so this is like you have the eventual output at the end, but then even like somewhere intermediate, you're getting the output. And reason being that, remember we did some tricks like early stopping and like making the gradients, like removing some of the layers and so on. So maybe this is like somewhat catering to that idea that maybe I didn't need to train all the way up there. Maybe I can get some results onto here. Yes. Yeah. So yeah, that's a very good question. So they do talk about that, like how the training methodology is. Yeah, so they do talk about it is like there are a few updates to the usual one because you will have a loss at every point, right? That's what like the idea that comes to my mind is that like you will have a loss function. But I think high level idea is that you actually propagate from here itself, and then you do combine the gradients some ways. So there could be different ways of like combining the gradients. But yeah, that's why they talk in detail about like how gradient descent is applied here. And most likely they use stochastic gradient descent. I don't remember because there is no way you can use anything else given the given the the length in the And only Google could have done this, to be honest, given the the amount of like intricacies that are there in this. But the good news for us is that we can pick this up and use it, right? So we have that good starting point and we can use it for our image tasks, which could be like some difficult image task, right? So that's the good news for us. This can be used as like a pre-trained network. They already trained it. You have a good starting point in terms of the weights. Of course, like in your task, if you don't need this, there are ways to just like remove these parts, these branches. This is just like an additional addition to the architecture. All right, yeah, that's a good one. So finally, first of all, I thought not to talk about MobileNet because we already talked about a lot of different architectures, but I thought let's like quickly go over that regardless, because these are like used a lot in like small scale tasks, and for like, these are more like, there is this constraint on certain devices of like not being able to use so much like computational power. So we can do certain tricks to our network itself so that we can do a good job of like learning, but still not like reduce the number of parameters that we are using. So that's the fundamental idea behind mobile nets. The first paper is the one that introduced it. And they talk about like the motivation behind it is like these mobile devices, obviously. And I'm going to show you what they do. Yeah, and so that's the name of the convolution. That's known as a depth-wise separable convolution. And it's different from the normal convolution that we have seen until now. So that's the only thing that you need to understand here, because this particular operation or this particular step in your convolution layer is the one that makes them so like faster as compared to other models. So let's actually look at the basic architecture, and that's it. Like if you're interested in the details, you can just like go and read that paper. But understanding the basic architecture, and specifically this depth-wise separable convolution, I think is important. Let's understand that. So there are two steps to what they're doing in this paper. So I'm just like referring to that paper. So I just picked this from there. Okay, so remember what we've been doing to any like image like this, like if it's a 6 by 6 by 3, and obviously 3 means an RGB, right? And so you have like this thing and this thing, right? And if I'm applying like a filter, like a 3 by 3, right? So let's assume that this is like a, and remember the depth should be the same. So let's say I'm applying one of these here. Now, if you remember what we said last time was that consider this as a cube, right? And so that cube is placed like everywhere, and then we do some computation, and then we get like a feature map, and we get like the first value. And then again, I apply a cube here, and then keep moving that cube depending on my stride, depending on my padding, and so on. And then I get like one value, right? So the number of computations that I'm doing, depending on the size of this filter, right? Depending on the size of my image and depending on the depth of this thing, right? This image, they are like quite huge. And so that takes a lot of time in training and like estimating all the parameters. So what we can do is we can do something that's known as depth-wise convolution. And why is this like different is because what I'll do is I'll just take this top layer, this top stack of this like filter, and apply this convolution only to this top part, like one by one here, right? And then I will just like determine these things, right? These values. So basically I'll have like one value for like this convolution being applied only to this top surface, not like a cube. Does that make sense to everyone, right? So I just picked the top one here, right? And then applied the convolution to the first one. Then I pick the second one and I apply the convolution to the middle one. But then the output that I'm going to get is going to be the second layer here. Remember, this layer in our normal convolution used to come from the number of filters. So that's what we are doing. And if you have like more than one filter, then you'll have to have like these separate stacks. So that's the fundamental idea. So I'm like doing a depth-wise convolution in the sense that I'm not like using the entire cube, but rather using each of these like in my depth as a separate convolution. So in some ways I have applied convolution, but I've not taken into account the entire image altogether. Rather, I've just like picked the R part and then the G part and the B part. So they are like in some ways separated, but still together. So it has reduced the number of computation, and you can actually see in the paper that they talk about that if the same task, let's say, was done for like the usual 3 by 3 convolution, the number of like total computational cost in terms of the number of parameters that I'm like computing is like, let's say 2160. Let's keep that as it is. If this was a normal convolution, let me just write it down, normal convolution. But let's see what happens in depth-wise. So in depth-wise, this entire operation will give like the computational cost as like 3 by 3 times 4 by 4 times 3, which is 432. But of course, we are not done yet. So I'm going to do another step here. So this is step 1, right? And so I got like this thing, this feature map. But just remember that I got these features, like different feature maps, not because of the number of filters, but because of the different R, G, B, and other layers in my input. So because of the number of channels, I got this output, right? I'm not done yet. I will apply another point-wise convolution to this thing here. For this thing, I'll apply a pointwise convolution, which is nothing but like a 1-by-1 kind of a convolution, right? So I'll apply a 1-by-1 convolution. And the whole point here, if you think about high level conceptually, I just separated this like this RGB thing. So in some ways, I lost the spatial footprint of the picture in some sense because I just separated the R and the G and the B, right? But then when I apply this 1-by-1 convolution, I'm like putting them together again, right? Because then this is going to be like a simple convolution that I'll do like a cube or a volume wise, right? So this combines and then the number of computations are pretty low. So what the paper shows is that in the second step, so eventually you get like a simple feature map of like 4-by-4 by 5, right? And the number of computation in the first one is depth-wise convolution. The second step is the point-wise convolution. And they're separated because if you remember in the normal one, we have them together, but this trick really works because in the point-wise one, I have like a 1-by-1-by-3 filter that I'm using. And then I have like 4-by-4-by-5 is my output. So if I just like compute this, this is equal to 240 computations, right? So the total number of computations is like 432 plus 240, which is like way, way less than this 2160. Right, so this is a very simple kind of comparison, but this shows why this depth-wise, why splitting this task of like a normal convolution to a depth-wise and point-wise works so well. And like, believe it or not, these 1-by-1 convolutions like are really helpful in reducing the number of computations you're doing in your network. You must have noticed that pattern that's coming up in like most of the architectures. Right, so as I said, this shrinks like the depth-wise plus point-wise, it shrinks the overall computational cost to like by about like 70% in certain cases, which is like huge. And so they work really well on like mobile devices, smaller devices, and when you don't have as much computational ability that you need to train these networks. And there are a few additions to this, and that's why I have like 2 papers, and you're free to read them. But I'll still go over like what are the differences and what are some of the additions that are there to the original MobileNet. And one of them is that there is this residual connection that has been added. So there are 2, definitely go over the papers, but I'll still show you the 2 different variants of MobileNet, just so that you're aware. Okay, so the first one is pretty simple, that like you get your image, whatever input that is, and that's a wrong spelling of image, I'm sorry. So anyways, and then you do the depth-wise plus point-wise. And you have these depth-wise and point-wise blocks together 13 times. So you have like 13 such blocks, right? And then finally you have like a pooling layer. So this was the original network, right? So you have a pooling layer. And then finally you have like the fully connected, as like similar to any other CNN, fully connected layers, and then a softmax. And obviously, you like just imagine in any image classification, you can have like softmax of 1,000 or more than that. Depends on the task, right? So this is the basic one. But now we have like an improved version, which is also known as, I think, MobileNet version 2. Where you have like the image, I'm just denoting by I, and then you have like these depth-wise, point-wise blocks. And in addition to that, you have like these residual connections. So that means when you have like these depth-wise, point-wise, you remember what a residual connection is? I can just like skip one of them and go here, right? So that has shown to, and remember why we used it? We used it to improve performance. And so that even adds to this network as well. So you'll have like 13 of these, sometimes 17 have also been used. And so you'll have like these skipped connections, right? And then again, this one, maybe skip by 2 and so on. And eventually you'll have like a fully connected and a softmax. So this is what this like other paper talks about, MobileNet version 2. And they are showing in the paper that it has like greater efficiency in terms of like the runtime and other things, because obviously you've subsequently reduced the number of parameters. All right, so those are some of the important models, and why do we need them? That's the question that arises. Another thing that before I jump into transfer learning, yeah, so let's actually talk about transfer learning. So we discussed many existing architectures, right? And you can tell just by looking at these, the complexity of these, that these are difficult to just like replicate from research papers. First of all, that's the first thing, right? If you look at a research paper, that's like really hard to just pick it up and replicate it. So there are like these open source, I don't know if you've looked at many of the repos that are available on Git. So you can just like Google some of these. If you see, let's say, a VGG network or like any network that you've come across on a research paper, you can just like Google them and find them on Git. That's one thing. So you can actually download that code. Most of these are open source. So that's good news for us. And most of them actually come with most of the frameworks. For example, TensorFlow and other frameworks, you can directly use them. And that's a fundamental idea of like transfer learning. So what you can do with transfer learning is you have the benefit of decreasing your training time because you can begin with one of the basic networks, right? So that's the fundamental idea. You can reduce time in a lot of ways, and you can reduce your like, if you start training a CNN from scratch, that takes in a lot of like different inputs from you, including the hyperparameters, right? And that question has come up multiple times. And because somebody else did that for us, we can use that as a base and go from there, right? Why to waste time? That's like my goal here. So there are some, okay, that's that. Let me see if I want to. Okay. Yeah, so that's that. And I think this section talks about how to do transfer learning in Keras with some of the known models. So I think they talk about 3 different ones, and we have covered all 3 of them. So it'll be easy for you to, yeah. So here are the 3 models that are, they're showing how can you like get started with these 3. For example, like the VGG 16 or 19, the GoogleNet version 3, Inception version 3, and then the residual network ResNet 50, again, like one of the variants of ResNet. So this like article actually shows you in detail how you can pick one of these up and then just like get started from there. High level, what I would say is that if let's say one of these models had like a final soft max, that's like 1000 outputs, and your task was just like a binary output, right? So what you can do is you can tune or update the final softmax layer to just like a binary output, right? If you feel that you have like way less like lower resolution images as compared to what were used here, because these are like high resolution images, right? So you can skip certain layers. That's also known as like freezing certain layers. And that is also possible. You can just like remove or freeze or not change those parameters some ways and then train on like a shallower network from there. But still, it provides those that good starting point. So you don't have to think much about like hyperparameter tuning and other things. So that's an important part. And another thing to improve performance that I think I forgot to put in the lecture notes, maybe I'll add it later, is data augmentation, because that's required in most computer vision tasks. So the issue here is that most of the times you don't have like huge data sets, right? And the good thing with transfer learning is that if you don't have a huge data set, you are already beginning with somebody's model that was trained on a huge data set. So you do have like a good starting point there. That's the first thing. And the other thing is that let's say you have like more data always helps in neural networks, but if you don't have it, then what to do? So then one technique is known as data augmentation to improve performance. And then there are many articles on that. I think I forgot to add them here, but like let me give you a high level idea. So let's say you have some images, but they're not enough to train a network. What you can do is you can create like more images from there, some kind of like sampling from the data that you already have. For example, so then the question arises, if I just like replicate the same images, then that's not really adding anything except the number because it's the same information, right? So one way is that if you're doing some kind of like object a classification, for example, whether this is a tree or not, and you have like some tree pictures, so you can create more tree pictures with just like by creating a mirror image. Because if you create a mirror image and that again, it's a tree, but then it's a different point in your like network, right? Those kind of things. Sometimes like rotating or changing the RGB. So let's say it's a colored image. So you have like 3 channels or depth, right? So changing the RGB values of that image, sometimes like sampling it from some probability distribution helps, because you have the same image, but you changed the color, or cropping the same image sometimes. Like random cropping can also help, because if it's a tree picture, maybe you cropped it, or like you shrunk it, or you made it bigger. All those kinds of techniques are there for data augmentation, specifically for computer vision tasks. And like one really intricate one, I remember. Okay, I haven't noted that down, but I remember like we can use PCA as well when we are doing the RGB adjustment in your color like channels. So you can like pick up based on your principal component analysis, you can pick up like what pixel values you want for like the R, the G, or the B. So there are many techniques that are available for data augmentation. And why I brought up that topic is because I know many of you are working on like image data for your project. And if you don't have a huge data set, if that's your concern, that you might want to look for like data augmentation techniques, because like there is a huge literature on that as well, right? Okay, so one last thing before we end today's lecture is object detection. And why I put that as optional is because obviously this course doesn't permit me to go over all that. If this was like a computer vision course, obviously we can go into the details. I have provided some links to the articles, one important paper, and implementation in TensorFlow. And I know that object detection is an important aspect of computer vision today, because you're not just classifying images, but you're also identifying them, right? So, and I know one of the teams is actually doing object detection. So these are some of the resources that might help you. High level, what we are doing in object detection is that just looking at the image and extracting information is not enough. We are also doing classification based on their location in the image. So what happens in the loss is that the loss function is based off of like you must have seen the bounding box. It's very common, right? The boxes that actually classify different objects. So if you've seen that, then you know that that's the extra addition to my prediction that I'm doing in my like object detection. So I need to predict that box as well. So the dimensions of those are also part of my like labels when I'm doing the learning. So that's an added part. Of course, like it's not part of this course, I couldn't like squish it somewhere. And so I have added this. And if you need like more help with that, I can help you go over that. But definitely looking at the implementation will help you, because this is like a very detailed implementation in TensorFlow that can help you like understand that. Okay. So yeah, that's all I have. I think everybody's like exhausted with like so many different networks. And like one closing like comment that I have is that you don't need to remember these networks by like with their what convolutions, what layers, how many layers, but just like no high level idea of like what is it adding to this research? What is it adding to my computer vision problems largely, right? And so based on that, you can pick your starting point for any problem that you're solving. Yeah. All right, so thank you so much, everyone. And I think we're meeting on Tuesday, right? Monday is off. Monday is off. Yeah, I know. I received an email